Welcome back to module 8 of the course Time Dependent Quantum Chemistry. In this module so far we have discussed light atom interaction, and we have shown that if we use first order perturbation theory, time dependent first order perturbation theory, where we are assuming that the population was in the end state and it's undergoing a transition from end state to the mth state, what would be the population at the final state, m state, after the perturbation is turned off. We have already shown that this perturbation, time dependent perturbation, which can be expressed in terms of the vector potential which is created by light when it's propagating through vacuum. So we'll move on, and we will now explicitly look at the terms. This is the population. This will give me population, actually square of the absolute value of this term will give me the population at the mth state. So what we are assuming here is that we had an n state, and then m state can be higher than in energy, higher than n state, or it can be lower than n state. It doesn't matter where it is. So we'll just assume that it is somewhere. This is another m state, and system is undergoing a transition due to this coupling. Due to this coupling term. When system is undergoing the transition, we will assume that the perturbation started, which means the interaction, light matter interaction or light atom interaction started at t equals 0, ended at t equals t1, and immediately after the after we turn off the perturbation, we would like to know what is the population. So we started with the population in the n state, and after the perturbation, after this interaction, what is the population in the m state? That's exactly what we are trying to find out here. So as I have mentioned that before, is that this perturbation part can be expressed in terms of this vector potential. Vector potential is coming entirely from the fact that the light is propagating through the vacuum medium, and when it is propagating through the medium, it is creating this vector potential. It is associated with this vector potential, and this vector potential is now interacting with an hydrogen atom, where I have, this is classical way of showing, I have a nucleus center and an electron orbiting the nucleus. But this is a classical picture, Bohr atomic model. But in the quantum model, it's going to be a cloud of electrons. So I have a nucleus, and then there is a cloud of electron around it, and there will be a place, position in the cloud where the cloud would be dense. Otherwise, it is like this. So this is the interaction we are looking at, and we are trying to find out what kind of transition we can have. So vector potential, once we express the perturbation in terms of the vector potential, one can write down this, insert this one here, and one can write down as minus I by h cut, then minus I by h cut, then I have this minus I h cut E by m. So this part is coming, then integration 0 to t1 e to the power I omega m n t, then this integration psi m this dot product multiplied by psi n 0 dt, which is nothing but minus, so this minus and minus plus, and then I square will give me minus. So that's why finally what I'll get here is this term will be reduced to minus E by m. That's the integration what we get. Now A has a particular expression we have seen. A will be expressed as, A is a vector, so A will be expressed as, and A depends on the position, so we will explicitly write down the position vector comma t. So it depends on position vector and t, which is nothing but A naught by 2. We have seen that it can be expressed, the real part of A can be expressed as, this is the real part of A, is expressed as A naught by 2 it is expressed as A naught by 2, that's the amplitude divided by 2, then the epsilon, this is the unit vector along the polarization direction, and then e to the power I omega naught t minus k naught dot r plus complex conjugate. That's the way we have already seen it. So if we insert that one here, we get now two terms. One term is minus E by m, we will write down, then A naught by 2 we will write down, then 0 to T1 e to the power I omega mn t, then this integration, then this A would be expressed as e to the power I omega naught t minus k naught dot r, then polarization unit vector psi n0 dt. So this is one term. Another term would be e to the power by minus E by m A naught by 2, then 0 to T1 e to the power I omega mn t, then this integration e to the power, now this CC complex conjugate, which means that's complex conjugate of this term. So it is going to be now minus I omega naught t minus k naught dot r, then epsilon this omega naught n0 dt. That's the, these are the terms we get, and this can be further reduced in a following way. I can write down E by m A naught by 2 0 to T1, then e to the power I omega mn plus omega naught t. This integration, this is an integration within the bracket notation what we have written, it is the integration over the entire space. So basically this is an integration something like this. I have integration over all, this is r vector, then psi m 0 star r vector, then e to the power this term would be there, and then psi n0 r vector dr vector. So it is the entire space. So I have, if I have a three-dimensional space, this is x, y, z three-dimensional space, and this is the r vector I have. Then r vector can be in any direction, and this r vector can be very conveniently written in terms of scalar, and in that case it is going to be r, then theta and phi. So either I have to express this integration in terms of vector, which is dr bar, or I can re-express this integration in terms of scalar quantities, which will give me the same result, which is r theta phi. So, this vector r vector can be expressed in terms of scalar quantities r, which is the distance from the center, and then theta is this angle and phi is going to be this angle. How to do that we will find out later, but the bottom line is that this integration or whatever is written in this bracket notation, that is the integration over the space. That is why this time part, temporal variation part, the time dependent part can be taken out of that integration, and that is exactly what we have done here. So, once we have done it, we will be able to just reduce it further to make it to get a convenient expression for our treatment. So, we have this this one, and then the integration is going to be e to the power minus I k naught dot r, then epsilon unit vector, then this is n dt. Then another term is going to be e by m a naught by 2 0 to t1 e to the power. I will do the same thing here also, omega mn. Here I have another t term, so omega mn, or I can actually take out the t term outside the bracket. So, omega mn minus omega naught t, then the spatial integration psi m 0 e to the power I k naught dot r epsilon dot this psi n 0 dt. That is the way we can write it down. And what we see that now one can find out one fact, that this integration, this is bracket, which what I have written in the bracket, this integration is over the space, entire space, over the entire R space, and R is a vector right now, and this integration is over time. That is why this spatial integration can be taken out, and one can write down in a following way. One can finally write down as minus e by m a naught by 2, then we take out the spatial integration as e to the power minus I k naught dot r, then epsilon dot differential operator, then psi n 0 dt. This is taken out, then integration is going to be 0 to t1 e to the power I omega mn plus omega naught t dt, plus then this integration psi m naught e to the power I k naught dot r epsilon dot differential operator psi n 0, then integration 0 to t1 e to the power I omega mn minus omega naught t dt. So, this is what we finally get after reducing the equation. We will further reduce the equation. This is what we have got already in the previous slide. We will further reduce this equation, but we will now focus on the time integration part first. So, together this time integration is, here I have plus, here I have minus. So, together I can express it together to instead of writing twice, I can actually express the integration as 0 to t1 e to the power I omega mn plus minus omega naught t dt. That's the integration I have. So if I do this integration, simple integration, we have already seen this kind of integration before, e to the power I omega mn plus minus omega naught t divided by I omega mn plus minus omega naught. This is the integration. The limit is 0 to t1. So what I get here is that e to the power I omega mn plus minus omega naught t1 minus 1 divided by I omega mn plus minus omega naught. This is what we get, because if t equals 0, this part is going to be 1. So now I'll just make one trick, and the trick is, this is a trick which we have used before as well. This is going to be t1 by 2, then e to the power I omega mn plus minus omega naught t1 by 2. We are multiplying by this, then I get e to the power I omega mn plus minus omega naught t1 by 2 minus e to the power minus I omega mn plus minus omega naught t1 by 2 divided by I then omega mn plus minus omega naught t1 by 2. We will be able to write this down this way. So if we do that, then we can immediately simplify e to the power I theta minus e to the power minus I theta. This can be written as cos theta plus I sin theta, then minus cos theta plus I sin theta. So I get 2I sin theta. Similarly, that we can express this as t1 by 2 e to the power I omega mn plus minus omega naught divide t1 by 2. Then this part is going to be 2I sin omega mn plus minus omega naught by 2. This is the sine function. Then divided by, I have I omega mn plus minus omega naught divided by 2 t1. So what I get finally is that t1, so this 2 and 2 will be out, this I will be out. So I get t1 e to the power I omega mn plus minus omega naught t1 by 2. Then cardinal sine function, which can be written as sin c omega mn plus minus omega naught t1 by 2. This is the cardinal sine function. So finally, what we are seeing is this time integral is giving me the response of a cardinal sine function, and we know that cardinal sine function is very steep in its behavior, and we will it's very steep in its behavior, and we will now insert this into this equation. So if we insert this equation, we will be able to. So this time derivative is now going to be a time integration which we had before, that can be replaced by this cardinal sine function. So when you replace this cardinal sine function, we get the behavior of the population. So finally the population will depend on this the response of a cardinal sine function. So that's exactly what we are looking at right now. So we'll insert it and we will see that this is now, I can write down as minus E by m a naught by 2, then I have this spatial integration part, I will write down as e to the power minus I k naught dot r epsilon dot derivative operator psi n 0. This is the spatial part, and then I have this entire function as the integration, that is going to be T1 e to the power I, then omega mn. Now because this is plus, so we will use only plus term, plus omega naught T1 by 2. This is one term, and then cardinal sine function omega mn plus minus omega, sorry, not minus, only plus omega naught, then T1 by 2. So this is one term. Then I have another term, and when we will writing the another term, we will have this is plus then this spatial integration e to the power I k naught dot r epsilon this n 0. Then I have this T1 e to the power I omega mn. Now I have minus term, so I am using minus term T1 by 2, and then cardinal sine function, which is omega mn minus omega naught T1 divided by 2. Then this entire thing is within the bracket. So we have two terms. This term, the first term, this one, and the second term is here. There are two terms which is going to contribute to the population in the mth state. And if we look at the behavior of the cardinal sine function, we generally call it like this way. It's a very sharp function. It has a value to very close to this 0 point. Otherwise, it doesn't have the value. So cardinal sine function, if we plot, it will be like this. This is the cardinal sine function value. It gets value at x equals 0. If this is cardinal sine function, then at x equals near x equals 0 to the limit x equals 0, it gets a maximum value, and it reduces. I mean, it goes to 0 very quickly, and when it goes to 0, I get x equals pi. So x equals pi value, I get the minimum value, and so we will find out how this cardinal sine function is affecting these two terms. This is term number 1 and this is term number 2. We have to check individually how these two terms are getting affected by the cardinal sine function, and remember, this width is very, very narrow. It's very, very narrow. It is only the cardinal sine functions mandates the values to be within a very narrow width.